Thank you very much for joining us. I know it's going towards the last part of the event, but I'm really excited, first of all, to be joined by Bram and James that will be joining me in presenting this session today. So, my name is Nikiforos Botis, and I'm a solutions architect working with public sector customers in Greece and Cyprus. But with me, I have Bram van Ginneken and James Meakin, who are from Radboud University of Medical of Radboud Center, and they will be walking us through what they have done on the second part of the session. Before that, though, let's start seeing what's in for us today. What's the agenda? So first of all, we'll be seeing why is it important and why do customers are motivated to adopt containers. Maybe it's already known for some of us, maybe not, but we'll do a quick overview of the technological solutions that exist within the AWS ecosystem in order to run and deploy and build containers at scale. And then we will see how, from the services, the building blocks, as we call them, in order to do that, we will see how we can try to operationalize this and where development meets operations and how we can do this at the containers environment. Before I give and hand the stage to our friends from Radboud University to explain what they have done using these technologies themselves. So starting with why are companies moving to containers? Why are they adapting it? And companies might be public sector organizations, might be universities, doesn't necessarily need to be obviously private companies. And I think we can all agree here, especially after what has been a long 2 years with the pandemic, that the only thing that we know for sure is that change is going to be here. There is changes in the societal environment, political, climate, all sorts of changes, obviously healthcare. And in order for organizations to adjust and still be relevant for their customers, their communities, they need to follow along. So when the business needs to change, obviously IT needs to support this change or even drive this change. And that's why many times it's not a matter of developing a new service, a new feature, it's a matter of reinventing a business. And that's why containers are very central to this change. So usually when we're talking to customers about containers and these technologies, what are they really asking us for? I think I'm yet to meet a customer who is telling us that I prefer to work on my infrastructure and scale it and patch it and maintain it and not build applications. And I think this will never change. We can be sure that this will not be a change that we will see. So focusing on applications, focusing on creating value, and not focusing on managing where this application runs. So this goes hand in hand with scalability, of course. How can we scale when we have some COVID platforms that people were booking their vaccinations, for example, and have millions of requests per second, per minute, per hour? How can we scale this, ideally without having to really procure many servers? And then, obviously, security is always here. And how can we make sure, especially on very sensitive projects, but at every project, that security is at the heart, not only when we are building it, but also when we are running it, when we are scaling it, when we are making it available to customers. So some of the benefits that containers bring to this situation is, first of all, the consistency, right? There is consistency. We might have multiple teams developing different products. They might be using different even programming languages. But we know that the key pillars, the key elements are there. And this consistency is very important. But also, autonomy is very important as well. Because without autonomy, without being able, from developing a new feature to making it available to a large scale of users, customers, communities, then we would have issues and we will have delays that in some cases are not even allowed. We cannot work without the new changes. So these two pillars of autonomy and consistency are the heart, but we can see some other things as well. Obviously, the speed, the agility. How can we get to release new code and release new features in days, in minutes, and not in weeks? So let's now see some categories. What are our customers building with those technologies, the container technologies? First of all, obviously applications, from web applications to backend services to IoT applications. All those things are or can be supported by container technologies. Many of the COVID-19 vaccination platforms around Europe or the world were powered by containers, and this allows for this rapid deployment and scalability. It's not only that, though. It's also when we want to create shared platforms, maybe for continuous integration, continuous deployment, for other sort of releases, and for maybe managing our environment. And these are also, or can be, container-based. And same goes for migration, and something that is very close to my heart, the machine learning part, that effectively many, many parts, even of AWS services, such as Amazon SageMaker, are really having containers at their very heart. For example, when we're talking about SageMaker, we can have either the built-in algorithms or bringing our own code, and this is done in form of containers for training or for inference. So we see that these are integrated, and obviously there is many more categories in many different, it's not just about building applications. And let's now see how this is done. What are the building blocks? How do we support these applications? How do we support this need covering from our customers in order to allow this? So here we've got some services. Many of you might already know them, many of you not. But this is the most important thing, is the choice of the right orchestrator. And the orchestrator choice might dictate further tooling and further tools that we will need or we choose to use in order to have our successful containerized application. At AWS, we've got two different kinds of orchestrators or managed services to run containers. And these are Amazon ECS and Amazon EKS, Elastic Container Service, Elastic Kubernetes Service. We see that even at the naming, they're very similar, and actually their functionality are very similar, but they also have some difference. And part of the next slides is to see what are the main differences, but what are the similarities as well. And most importantly, how, if someone is starting today to build a containerized application and environment, how would they go about choosing what is the right one for their needs? So starting with Amazon ECS, this is probably the one that is, as we call AWS, opinionated way to run container at scale. But this supports a lot of integrations with other AWS services. It's even part of many other AWS services. And this allows companies such as Samsung, General Electric, Duolingo, and Expedia to build and run their applications on AWS. Things like Docker, and whoever is familiar with Docker, this is the service, this is the go-to service for having a managed control plane, and then having the compute type that, again, it's up to us to choose. I will say more on that in a second. And here we see how Amazon ECS, as the orchestrator, we see at the very top, can be used with different compute types in order to run it. And when I say compute types, I don't only refer to the cloud, maybe virtual machines in the form of EC2 instances, or AWS Fargate. We will also see more about the serverless way to run containers in a minute. But even at the edge, maybe it can be also on premises with Amazon ECS Anywhere that was just released a few months ago. So what we see here is that this flexibility allows for us to, if we have agreed on using ECS, to still have a uniform environment, even if we have applications that run both on the cloud and locally. Maybe we have something running on premises and something on the cloud, maybe at the edge. All those things can still benefit from Amazon ECS, and this way we have less change when it comes to our IT environment. And it's important to also mention that we've got the other services and integrations that will be visible on this diagram, for example. And we see so many other of the AWS services that we might know and we might have used in other contexts, maybe in CI/CD, maybe when we're building our applications. So we see here that ECS, Amazon ECS, is just part of the whole picture. And even within the environment of running, the compute environment, we can choose whether it will be EC2, maybe Fargate, maybe even local zones, the hybrid model. So moving on, the other side of the orchestrators, the two possible orchestrators, is Amazon EKS. So here, the significant change is that we're talking about Kubernetes. And by talking about Kubernetes, why would someone go for Kubernetes? It might be because of its very vivid community that exists around it. There is many open source and communities that can support questions and answers and meetups and all sorts of things. So this flexibility that Kubernetes is allowing makes it a very popular tool when it comes to containers. And Amazon EKS comes here to make it a managed service, at least the control, the assignment of containers to machines. so that we can focus again on the code, or we can focus on our applications and not on how we assign the code to containers, how we assign containers to machines, etc., etc. Here, we've got companies like Intel, Snap, GoDaddy using this at scale and hundreds of deployments at even within weeks in order to achieve that. Similarly, as with ECS, we've got many different ways to run EKS on AWS. It doesn't need to be on AWS. Maybe we want to do it with anywhere or with the open source EKS distribution or distro. We can run it on our hardware. So again, we see that this flexibility is a common thing between the two orchestrators. And based on our needs, we might go for one, or we might go for more than one. Again, hybrid, maybe modernizing a legacy application would make us run something on premises and something on the cloud until everything has moved to the cloud. And similarly here, what we see is, compared to the previous diagram, is some differences when it comes to the specific tools. And here we've not got so many AWS services like before. We had code build and code commit and all those sorts. Here we can have GitHub and Jenkins. This does not mean that in one case, for ECS, for example, this could not be possible, or here that we could not use, or we cannot use AWS services. Of course, it's possible, but what this slide tries to show is the flexibility that we can achieve with EKS. And it's not only on using GitHub and Jenkins and all those version controlling or build services, but even other for networking or service mesh, the app mesh that AWS has launched, so that we can have the networking done, and we can have the multiple containers communicating in a secure way, we can have full visibility, etc., etc. So we can see all those different parts, and even with the newly launched controllers for Kubernetes, or ACK, I think this is a couple of years old, which allow for us to access other AWS services through these APIs, through Kubernetes APIs. So this makes possible to use EKS and have access to other tools that we might already use. So just to summarize, what are the compute options that we've got for both ECS and EKS? We can see that we've got Fargate, and I will explain, as I promised, in a bit, what this is all about. We can have Amazon EC2, which is the most traditional way, the VM, the virtual machines on AWS. So we can definitely have EC2 as a launch type for both ECS and EKS. But we can also have them running at the edge with local zones. We saw an expansion on the local zones during the last reInvent, wavelength for 5G zones, but also on premises, either outposts or even with anywhere. So we don't need to procure extra hardware for this. And here, what we usually call an unsung hero of all those applications that are container-based is where do we actually store our code? Because it's important to have the applications that are, or the services that are responsible for running and deploying and maintaining, etc. But where do we actually store it? And then we still get the benefits of version control, we still get the benefits of not losing it, of course, etc., etc. So this is where Amazon ECR, or Elastic Container Registry, comes into play, which is a service that effectively leverages all the benefits of Amazon S3 when it comes to durability and high availability, the 11 nines, because it is using Amazon S3 in the background, but it's used for storing and uploading images. I think here it's worth mentioning that we've got 8 billion image pools per week globally with this service, so we're talking about a big scale, and it's not only being used by ECS and EKS that we described. It's used even for light sail, like just deploying a little website, a little blog, or other services running containers in the form of a Lambda function, or AppRunner for running web applications that are container-based. So all those sorts of things can leverage Amazon ECR and its durability, availability, and low cost in order to have the code stored locally, securely, and durably. And having talked about Fargate a couple of times now, AWS Fargate is the second launch type when it comes to containers, ECS and EKS, when we're talking about cloud deployments, of course. And this is what we call a serverless way of running containers. With that, I mean that here we are not choosing a specific instance type, we are not choosing characteristics and what is a specific family of the instance. We are just choosing a number of vCPUs that we expect or we believe that our code will need. But then the scaling, when we have more traffic, obviously it scales up. When we have less traffic, it saves us cost by scaling down. And when I'm talking about scalings, it's also, about savings, it's also part of what we call savings plans. So if someone has commits to a certain number of dollars per hour, then this can be spent towards AWS Fargate or Amazon EC2 or AWS Lambda. So here we can really do some cost optimization, but most importantly, we can leave aside choosing the hardware, choosing the specifications of the servers, and leave that to Fargate, to AWS Fargate to decide. And then talking about containers and compute, we covered it. We covered how this can run. Here, let's go a bit more deeper when it comes to storage. And we know that different containerized applications, based on the initial description we made of different types of applications, have different needs. And the ephemeral storage that comes with every instance might not be enough, because we might want to scale and have storage shared across more than one availability zones to not lose a state, to make it highly available within and across availability zones or even regions. But even here, we might want to have a file system that scales, a file system that stores our data persistently and are not getting lost after every training job runs, if we're talking about machine learning. So here, two services that come into mind quite easily for people who are used to working with AWS might be Amazon EBS, Elastic Block Storage, for attaching block storage to Amazon EC2 instances, or Amazon EFS, the Elastic File System, that again scales automatically. We've got even a new storage class for infrequent access so that we can do some important cost optimization there. So we see that different applications might have different storage needs. And obviously, there is no one-size-fits-all solution, even when we're talking about storage. It's up to the application and up to the needs of it to decide what is the right one. And then the last thing that I wanted to touch upon when it comes to how to build and run container applications, we covered compute and storage. It's also networking. Networking is very important when it comes to, of course, security. Of course, making different containers able to communicate with each other. We don't want them in isolation. That's why they're multiple different per application to be able to communicate. So VPC, Amazon Virtual Private Cloud, is the obvious one, because without the VPC, we cannot launch an EC2 instance. We cannot successfully run an application. But it's also how these containers will communicate with each other. And the proxies that can be installed on the instances with AWS AppMesh using the Envoy proxy protocol, then they can scale, they can have visibility over when one instance might have some issues, one container might not be able to be reached. So AWS AppMesh makes it very easy at an AWS environment. And of course, scaling the traffic, either using layer 7 or layer 4, if we want application or network load balancer, is also another option that we need to take into account. And now, let's see and kind of change a little bit gears and go more into, OK, so we know that we can build an application. We know that we have the right storage. We can have the right networking environment. How can we allow different teams to build their applications, to have deployments maybe daily, maybe weekly, without making a mess, without even putting our security in risk? So here we see that the classic problem of a monolithic application is that there is one deployment pipeline, and even if different teams have different patterns, one team might run faster, the other might not, then they still need to go through the same deployment and delivery pipeline. And this comes with some obvious challenges that I won't go deeper at. So what we can see, and this is one of the benefits of containers and microservices, is that this can be split per team. So teams that are able to deliver faster, they deliver faster, the rest not. And as long as the APIs and the contracts are met, then everything can communicate with everything else, even without having the same delivery, the same deployment pattern. The question here that comes to mind is, OK, so if I have different teams, different developers doing different things, maybe using different technologies, how will I ensure that some things remain the same? How will I ensure security? How will I ensure quality of the deployments, et cetera, and many others? And this is what we can tackle, the problem of having some things that are centrally dictated or centrally set in 3 different ways. We would allow everyone to do whatever they want. This has some advantages, but has some disadvantages, and might create a total chaos if, of course, things go wrong. If we have a very central control, if you have a team that everything passes through there, then we're probably getting into the monolithic problem of having very slow deployment, of waiting many things before we actually deploy, before we actually scale. So something that comes, and is probably sitting in the middle of these two, is the notion of guardrails. And if we try to define guardrails, we will see that these are mechanisms that allow to put some certain things that are probably applied to the whole organization, the whole team, the whole development team. And these help us reduce the blast radius. So even if something goes wrong, it remains within a small area. It can be tackled and resolved quickly. It doesn't affect the whole of the application. So this can apply to security, of course. This can apply to other things. We can help us monitor better, or provision, or deploy applications. So this notion of guardrails, and I think the previous session here was on Control Tower, AWS Control Tower. So whoever was here before, or whoever is familiar with AWS Control Tower, guardrails is at the very core of Control Tower. And this is not per application, this is per account, or per AWS environment. So this really helps. And some of the guardrails, security-related, might be to not allow, for example, public access to any S3 bucket. And this can be done centrally, or to have CloudTrail enable AWS CloudTrail for storing logs of every API call at every account, and without anyone being able to change it. So these sort of rules can be applied at a central level, affecting all teams, and also are usually expressed as code. So we don't need to have other types and overcomplicate things. It can still be expressed as code. So now, I think is a time to see some of the things that we mentioned in action, and how Radboud University and Bram, who will go first, to show us how the Grand Challenge platform was built. And we'll actually work backwards, following a true Amazonian fashion. We'll first see how it looks like from Bram, and then from James we will see how all the services, or many of the services we discussed before, were leveraged in order to do that. So it's my great pleasure to welcome Bram on stage. And Bram, the floor is yours.
Thank you very much. Yeah, I'm very happy here to talk about a platform that we have set up in my research group, and how we built that and what the requirements were. So I'm going to show the platform from a user perspective. So I'm a professor of medical image analysis. I have a research group, and people in my group develop algorithms that analyze medical data like scans or pathology images, so that eventually tasks that are now done by humans can be taken over or supported by computers. And what I've learned while running this group for many years is that if I have a PhD student working on a particular problem, like segmenting the kidneys in CT scans, there are actually other people all over the world working typically on the same problem. And then we publish papers about it independently, where we say, okay, my system is better than all the previously published systems, and you cite some numbers from the other publications, but we don't really compare our algorithms to each other on the same data. We don't really collaborate together. And I think this is actually what we should do. It would be far more efficient if researchers all over the world would collaboratively work on solving certain problems. And for that, we built this platform. So if you go to the website, you see the platform, and it's about challenges and algorithms and a couple of other things, because over time we try to put all the steps that you take when you're developing an algorithm into this platform, so that everything can be done in a web browser. And before you can actually start to train an algorithm, you need to typically annotate data. And you also need to compare your performance of an algorithm on certain data sets with the performance of a human expert, a radiologist. So you need to organize a reader study. So we built that kind of tooling into the platform. So for example, this is a reader study that we developed when, in the early days of the pandemic, when CT was important and there were no other treatments. So COVID patients in a hospital often got a CT scan to see if they actually had COVID and what was the extent, the severity of the disease. And a group of radiologists in the Netherlands developed a scoring system. How should radiologists report on these CT scans? It was a new disease, so nobody really did knew how to do that. So we set up a training module so that radiologists could learn how to interpret these CT scans. But we also used that reader study to actually measure how a big group of radiologists scored these scans. So people can sign up on the platform and then open this reader study. And if they have access to it, they can press a button, they launch the reader study, and then they get a medical viewer in the web browser where they can scroll through the data, and in this case, answer a couple of questions about the scan. And we use that to actually very quickly compare the scores of a large group of radiologists from the Netherlands, all web-based, so we couldn't leave our house in the early days of the pandemic. So we could quickly publish a paper to show that this scoring system that was developed by radiologists was actually consistent, and radiologists agreed with each other on what they were scoring. So then we could quickly publish this paper in Radiology, and this established this scoring system as the worldwide accepted scoring system for CT scans of people suspected of COVID. And now that we had the clinical standard established, so we had defined how radiologists should score these CT scans, we could start to develop an AI system to do exactly the same. So that is what we did then later, and we put that as an algorithm, as a container on the platform, so that everybody in the world could now use this algorithm. They could upload their own CT scans and look at the results of the algorithm and compare that with their own scores. So once we put the link to this algorithm in our radiology publication, we saw that immediately radiologists from all over the world, from South America, from Asia, from America, from Europe, started to upload CT scans because there was really a need in the early days of the pandemic for these kind of tools. And then we also realized if we want to build these systems that are used by people all over the world, we need a cloud platform to run it on, right? So what you do is, when you get access to the algorithm, you have a number of things to choose from. There's a setting container. So if you are the algorithm developer, you can upload new versions of your algorithm to the system. And it's also possible to link it to a GitHub repository. And if you tag the repository, automatically a container gets built for you. So you see that over the time, we have developed a number of versions of this algorithm. But if you are a radiologist and you want to try it out, then you can upload a CT scan, and then the algorithm processes the scan, and you can view the results. You go to a page where you see the results that have been processed, and you can click to view them. And then what happens is a container is started, and in your web browser, you can now view this CT scan with the output of the algorithm. The algorithm in this case has segmented the lobes in the CT scans and has highlighted all these regions that are abnormal, and from that a severity score for this particular patient can be computed. And this has all the functionality that radiologists expect, so they can turn on and off the overlay, they can view the image in different directions, scroll through it. And to do that, we need to run this server-based, so we need to make sure that the users, which are located all over the world, have a server nearby where these images are rendered, otherwise you get latency. So we basically had to make sure that these servers were all over the world. This one is from the Frankfurt region. And we have then, after we had developed that, made our data available so that others can also develop their version of the algorithm on the same data. And that's what you do when you organize a challenge. And now we're a bit later in 2021. We're actually at the moment running another challenge for COVID-19 CT scans using a database from France, where in a national effort they have collected 10,000 CT scans of patients who've actually developed severe COVID or not. And the idea is to try to use a CT scan to predict which patients will develop severe COVID. And people can participate in here, download this data set, and develop their own algorithm for that. So they can form a team if they want to work together. And then if they submit an algorithm, a score is computed and they end up somewhere on the leaderboard. We can hand out prizes. But for me, the most important thing is that these algorithms are now immediately available on the platform so others can use them. So in this way, we have closed the loop for this whole sort of worldwide development platform. And we have a lot of users. We started with this in 2012. We have 70,000 people who have registered on the platform. We have been running a lot of challenges. You see there's 126 public challenges, but there are also a lot of private challenges. So also for internal research projects, we run them as a challenge on the website so that when the paper is published, you open it up so that the rest of the world can see if they can build a better solution for this question. And we have a lot of archives now, more and more algorithms. So yeah, we really realized that as this is getting very successful, we need a very scalable way to maintain this website and to grow this further. And James is now going to explain how it works behind the scenes.
Okay, so thank you, Bram. My name is James Meakin. I'm the lead research software engineer at Radboud University Medical Center in the DIAG group. So the research software engineering team at Radboud, I think we have like quite a unique thing within academia. So we're a team of 7 research software engineers, and we're kind of entirely product focused. The 2 main products that we work on are grandchallenge.org and the Cirrus Viewer, and both of these things Bram just showed you. So grandchallenge.org, this is our platform that connects researchers and clinicians for the development of machine learning solutions in medical imaging. What we see this as is we see this as providing the deployment guardrails for both our developers who are deploying the Cirrus Viewer workstations and for our worldwide community of data scientists who are deploying their trained machine learning solutions onto our platform. It's an open source Django application with a multi-region deployment on AWS. And for Cirrus, this is a browser-based workstation that provides the clinicians with the familiar tools that they need in order to view and annotate medical data. This itself is a proprietary Vue.js and Mavis Lab application, but is deployed to grandchallenge.org. So we use containers everywhere on Grand Challenge. Everything you see is running in a container. And for this, we're using ECS in 3 different modes, and I'll go through these 3 different use cases with you today. The first is our API layer. This runs on AWS Fargate and with Fargate Spot as well. For our viewing containers, these run in multiple regions on ECS on Amazon EC2. And finally, we run algorithm inference using ECS on Amazon EC2 with NVIDIA GPU, and then this is different from the other 2 in that we're using ECS tasks rather than using ECS services. So our deployment architecture looks something like this. For our API, it's a basic 3-tier web app. We have our data layer, which is S3, RDS, Postgres, and Elasticsearch Redis down at the bottom. In the middle, you have our Django API, which is in a Fargate auto-scaling group on ECS. Any static content is going to be delivered from CloudFront, and any dynamic content delivered by Django. I started working on this project in 2017. You know, the grandchallenge.org platform, it's been around since 2012. And I immediately started with kind of modernizing this and bringing this into containers so that we had this sort of nice developer velocity and reproducible environments between development, staging, and production. But we were deploying on-prem. We were using Ansible to deploy this to servers in our data center on-site, using Ansible and Docker Compose directly. In 2020, when the pandemic hit, we were getting increased users from an increased number of collaborators from abroad in multiple regions around the world. And so we decided to do a lift and shift onto AWS. This has been sort of super helpful with scaling out the platform because, again, prediction of how much demand there's going to be for research software is super difficult to predict. On-prem GPU, kind of tricky. AWS is handling all of this for us. Moving to ECS Fargate, well, for our developers, this was really familiar to them. You know, we were already deploying this using Docker Compose files, so converting this to an ECS service is super simple. The API is very, very similar. And it also allows us to sort of pick, the bits and pieces that we need from AWS. So we're heavy users of GitHub and GitHub Actions for our CI/CD. And so all we did to change was we deployed our container images to Amazon ECR Public. Again, it's an open source application. And then we were deploying everything with open source Terraform code onto Amazon itself, AWS itself. Our monitoring we do through CloudWatch, which again, less stuff for us to maintain. And for our API layer, we could scale this out by monitoring CPU metrics, but honestly, our API traffic is not actually that big, so we just scale out our containers just as we need them. Where we do need to auto-scale is where we have asynchronous tasks. And so for our asynchronous tasks, what we need these for is whenever we need to do any heavy lifting, we want to get these out of the request-response cycle. So our main use case for this is in medical imaging. Someone uploads a data set, you want to do some quality assurance on that. That QA process, that can take a couple of hours and take up to 30 gigabytes of memory as well. And so because of those large requirements, we can't use Lambda functions for this. So we're using Salary, which is a Python library for defining a distributed task queue. That allows, which we then deploy the Salary workers, which then actually do the work onto Fargate. So these now don't have a connection to the outside world. They're just running on an auto-scaling group, connection through again to our data backend, and integrated with a simple queue service from AWS, so that whenever we have a task, we post a message onto SQS. A Salary worker will pop the message from the queue, do the work, put the results in the database, and then fire off other workers. What's nice here is that we can use Fargate Spot to keep costs down as well. So to scale this stuff out, it's sort of super simple. We need to define three things. First, we need to define a target, so an auto-scaling target. That is, what do we want to scale? Then we need to define a policy, which is how we want to scale that thing. And then we need to define an alarm, which says, okay, well, when do we want to fire that policy that scales that thing? So to scale out our Fargate workers, we define something super simple. This is just a bit of Terraform code. What we're looking at is we're scaling the desired count of our ECS service that runs our Salary workers. We can define a minimum maximum capacity, so we can scale to 0 when there's no work to do. And then whenever this target is hit, we want to change the desired count to either increase or decrease the number of services that we have. To scale out our workers, we define a policy. Again, we're linking through back to our auto-scaling target, and here we're using step scaling. And what we want to do is every 3 minutes or so, when our metric is in alarm, we want to just adjust the number of containers that we run by 1. So just increase until our metric is satisfied. And then the metric, because we're integrating with SQS, we look at the number of visible messages on the queue. If there's a visible message on the queue, then that work isn't being picked up by a worker, so just start more workers and take the message off the queue, do the work. Then what we need to do is we need to scale in, and so we're using CloudWatch again for that. You can do some very basic arithmetic and some conditional functions in there to define the metric to scale your things in, and we're just looking, okay, are there workers which are not doing any work? If so, take some out of the pool. So our next use case is for our viewers. And these work slightly differently in we want to deploy these into regions which are very close to the user. The viewer container is very latency sensitive, so we need this multi-region deployment, and it's very heavyweight as well. So each user is going to have around 8 gigabytes of data in memory. This underlying software that we're using, it isn't really designed for multi-user stuff, and so what we decided to do is launch one container for each user. Fargate is super nice, because you can tell Fargate, okay, hey, take this container and just run it. I don't care about where you run it. Just give me a network interface that I can communicate with it to. But it has a downside that it takes 1 to 2 minutes to start up a new container because the container image needs to be pulled to wherever the container is going to run. So what we need to do in order to start these containers quickly for the user is we need to run ECS on EC2 with an EC2 pool that we manage. We can then pre-pull the image to the container, and then when a new user comes in and we want to start that container for them, it's super fast to launch. So I'm going to replay this video again, and then what you'll see is it determines in what region they should launch the thing, starts the container, now the container is started. And then you can connect through, and this offers up a WebSocket connection through to the user so that they can interact with the data. So this is quick enough for our needs, and using EC2 provides this sort of flexibility where we can quickly pull the containers down. What we now need to do is we do need to manage the EC2 compute pool that this is running on. So now the viewers are going to run on this EC2 spot instance auto-scaling group. So we need to scale this out if that gets too small. So how do we do that? Again, it's super simple. We attach our EC2 auto-scaling group to our ECS capacity provider, and we set this variable here, manage scaling enabled. Then if a user comes along and ECS cannot place our task within the compute pool, it will start another EC2 instance up and place the container there. And we can have pre-warm instances and things like that, so we don't never run out of capacity. And again, this handles in scaling in as well. So completely hands-off for us and our developers. Our final use case is, up to now, we've always been running services. And so the final case is for running algorithm inference, which we use ECS tasks for. So we could use SageMaker for this, but we have around 3,000 existing models that use a different API. At the moment, Fargate doesn't support GPUs. So again, we're using EC2 with GPU nodes with the ECS AMI, which is optimized for GPU use. Again, scaling is hands-off for us. We just place a task onto the ECS pool, and then that gets executed for us. So the process that this happens is we get a message from Salary. It requests task execution onto ECS, which then puts the task onto the EC2 auto-scaling group. What the task then does is this produces output on EFS that we then need to pick up. And so what we do is we integrate this with EventBridge, which is for whenever a task is stopped, it will produce a JSON event. We can do a transform in EventBridge to put this message onto SQS into a message format that Salary understands. So then it integrates back with all of our existing code. And how we do this, we define this input template for our CloudWatch event. And what we define is we have this task which is defined within our Python codebase. And AWS will substitute in the ECS event to say that, oh, hey, an algorithm produced an output. You can now go ahead and pass the outputs from that algorithm and present that back to the user. So that's the story of our migration to ECS. It's been sort of very easy, very hands-off, and now provides the sort of the scaling that we're able to take advantage of for our research. I would like to thank my superb team who helped me develop this application, and thank you for your attention.
So thank you very much, Bram. Thank you, James. I think it's really interesting to see how what we described in the beginning can all come together, and the flexibility of using different versions, different launch types on Amazon ECS, for example, based on the needs. So different use cases, different needs, and thus different tooling used. So trying to summarize what we saw today, I think the orchestrator is the first thing, ECS or EKS. Then it's a matter of where will we run it? Will we run it on premises? Will we run it on a hybrid, maybe on the cloud? And if it's on the cloud, is it Fargate, is it EC2? So this is another key decision point to make. And finally, we saw how guardrails can be put and how they can be enforced if we're using AWS Control Tower, for example, so that we really ensure security, scalability, deployment, and quality along those processes. So as we wrap up, I think you've seen the slides, this slide again before, but I think what is really interesting is that here there is loads of videos that are specific to containers, either ECS, EKS, Fargate, of course, and a lot more. And then you capitalize on this and maybe get a certification. The ones that are more related to containers, I would say, is developer associate and DevOps professional. So they are there for you, and hopefully some interesting things you will learn along the way.